I know I can't but I'm very confused with it. I don't know why. I don't know how I'm getting confused with it.
Do you have time after class, or do you have any free time?
Yeah.
You want to talk about it after class? Okay. Okay, so you don't know how what?
How long you stay after?
Oh yeah, I've got time.
You got time?
Yeah, okay. All right, so please turn in what you have. Just set it up here, please.
You taking quiz redos?
Remember yesterday? I said you either turn it in now or turn it in next class.
Oh, I'm talking about the old quizzes.
Oh no, they're not redos. It's if you had a
If you
some
had
of
it, but it wasn't in the.
it wasn't in the grade book, but you can bring it next time if you don't have it today. Yeah. Okay, we need to get started. It's been harder for me to get here from across campus lately. I apologize for eating up time. So do you all remember what we finished class with last time? I was trying to get you to think about something. Inverses. Inverses. All right, has everyone turned in what I asked for? It's now or never. Good. If you did not check your grades to see if something was missing, you can do that next week, or it doesn't have to be today. I need that, pretty soon so we can get that squared away. All right, so we are talking about inverses today. The inverses of the trigonometric functions. And I'm going to do a little bit of a review of inverses, just at least graphically. We are in 8.1. Yes, 8.1. All right. Here we go. So inverse functions. Review. And I say review because you should have seen this in college algebra. So visually, with a picture, and I put this on the board last time, you have this normal picture of a function f. And we like to call this part of f, or this part the domain of f. I'm going to put dom f. That's the domain of f. That's the things that you can plug into the function. And then you have the stuff that comes out, which is called the range of f, which I'm going to put ran f. That's pretty standard notation for domain and range. So the input of f is here. The output of f is here, right? The inverse function goes back and takes everything back to where it came from, and we use the little notation with the little -1 on it. Not to be confused with x to the -1, which means 1 over x. This is one of those times in math where we have the same symbol that represents two different things. So if you see a little -1 on f like that, that means the inverse function. If you see x raised to a negative power, it means 1 over x. So it is a little confusing, all right? This is not 1 over f. So here, this would be the domain of f inverse, and this would be the range of f inverse. Right? Because f inverse is going to take stuff from here and send it back. So the stuff over here is the domain of the inverse, and then the stuff over here is its output, its range. So notice that when you have a function and its inverse, the domains and ranges switch places, right? They switch places. So you could say that the range of f inverse is actually the domain of f, right? The range of f inverse is the domain of f. All right. Now, this is the actual definition, all right? If you want the definition of an inverse, still reviewing. A function f is said to have an inverse called f inverse, like this, all right, if the following two conditions are true. You have to have these two things happen in order to be able to say that a function has an inverse. F of f inverse of x equals x, and f inverse of f of x equals x. I don't know if you remember seeing this in college algebra, but it meant that if you did the composition of the functions together, that when you plugged in x, it would spit out x. And it didn't matter which way you put those two functions together. So I'm not going to get into this algebraic explanation. It's just if you want to be precise, that's the actual conditions we need. Now, visually, I'll show you this visually. And you know what, I should probably tell you what this means, just in case you don't remember. This means f, and then inside of it, f inverse of x. And this right here means f inverse, and inside of it, f of x. That's what that little O meant. It's composition, functional composition. So if let's take a look at this first picture. Let's say somebody gives me a value of x, right? Well, that's great. Somebody gives me a value of x, and I first put it into the inverse function. That means the x would start out over here. And it goes through the inverse function, right? And comes out over here as something, I'll call it y. All right? So that would be this piece right here. That's y. That's x going into the inverse, right? Comes out as y. Now if I take that y and plug it back into f, so I take that y and send it back. So this x went over here. Now that y goes back. Where must it land? Where must f take that y to? Well, according to this, where does it have to land? Back on x. Okay? So it's kind of like this little loop. X goes into the inverse, goes back, and goes back to x, exactly where it came from, right? You need that condition to hold for every x you could ever pick over here. That has to hold. And then this condition, which is a separate condition, means that let's say I start my x off and it goes into f first. So now my x starts out here. It goes through f, comes over here and turns into a y. So this right here together would be y. Now I take that y and plug it into the inverse, so it's going to go back, and where must it land? Back on x. And that has to hold for every x that you started with over here. Yeah? That's the visualization of what inverses do. Now, I had started talking about an example at the end of class that I want to kind of pick up on and continue with. And it was this example of the function f of x equals x squared. And we had talked a little bit about whether or not that function had an inverse or not. And do you remember what we had determined? That it didn't, right? Because if I graph this function, right, it was a parabola, and we said that this would pass the vertical line test. Vertical line test is what we use to test to see whether or not something is a what? Vertical line test. A function. And then it would fail the horizontal line test because it would hit more than one time, right? And we even did a t-table. Remember the little t-table? Let me show you that t-table drawn like a picture, like over there instead, though. Like this. If this is this function f, then where did 2 go? Where does 2 go through that function? It gets squared, right? And turns into what? 4. Okay. Now, where would the inverse function have to take it back to? 2, right? And then if we plugged in -2, where would it go? It would go to 4. But see, if it goes to 4 also, how does this function know which one to take it back to? Does it take it back to 2 or does it take it back to -2? And there's no way of knowing, and it would fail to have an inverse. Understand? But the horizontal line test is what tells us that. Do y'all get why the horizontal line tells you that? Or is it just like it's the test and who cares? It hits 2 points. So let's take a look at that. If I plug in 2, I get 4, right? But I also can plug in -2 and get 4 here. So if I have 2 values coming out that are the same, then they had to come from 2 different x's. And so you don't know which x to send it back to. That's the idea behind the horizontal line test. If it fails the horizontal line test, like this one did, then it doesn't have an inverse, right? But I told you last class, the sine function fails the horizontal line test like really bad, right? I mean, you just draw a horizontal line in here, and it's going to hit like infinitely many times. So how do we get around that? Well, I'm going to show you how we get around it here first. Because if we're going to be able to handle this, we better be able to handle this, right? So if I asked you to go from 4 back, you know that you would need to take the square root, right? It's just a matter of would it be plus or minus. So I know that the square root function is the function that should undo this function, but the square root function does not have the ability to determine the plus or minus. So what I do is this. Here's how I fix this so that I can have a nice defined function. All I do is I come over here to this original function and I can cut the left side of it off. All right? Now to do that, what I need to do is restrict my domain. Right here for this function, I want the domain, I'm going to tell everybody right now that I only want x to be greater than or equal to 0. So it's like I'm telling you, look, draw this picture, but only plug in values of x that are greater than or equal to 0. That will only draw the right side of the graph, and if you look at just the right side of the graph, it passes the vertical line test and horizontal line test, right? But I had to restrict the domain for this to work. With me? So if I do it this way, this should be the inverse function. It should take everything back to where it came from. And it's never going to have to worry about taking things back to negatives. So look, if you plug in 2, it'll go to 4. Square root of 4 goes back to 2. If you plug in 3, where will it go? 9. And if you take the square root of 9, it goes back to 3. Make sense? Now that's one option. I actually don't have to do it that way. I could have cut that function off a different way and still had a nice well-defined inverse. How could I have done this different with a different cut of that graph? Take the left side of it, right? Instead of the right side? So look at that. I could have, if I wanted to, taken a different example, take the function f of x equals x squared, this time restrict the domain to be x less than or equal to 0. Then if you draw it, you're only allowed to plug in negative values for x. It's just going to draw the left side of the parabola. How would the inverse function change, though? Because it does change. How would the inverse function change? Is it still the square root? Of x? Think about it. Think about it in terms of this picture. If I plug in, I need to plug in a value here, right? And it has to be a negative value or 0. So if I plug in, let's say, -2, where is this function going to send -2? To 4. 4 needs to go back to where? -2, right? So how can I get that to happen? Negative square root of x, right? Okay, negative square root of x would work. Because what I'm going to do is I'm going to take the square root of 4, right? I put 4 in here, take the square root, but then return to me the negative answer. And that will take it back to -2. If I plug in -3, what's f going to do to it? Square it, it'll spit it out as a 9. And what's my inverse going to do? Square root of 9, 3, and then make it negative, so it takes it back to -3. So do you see how with the x squared function, with no domain restriction, I can't talk about an inverse. But with proper domain restrictions, I can talk about an inverse. And that's how we're going to do this with sine and cosine and tangent and all of them. We're going to have a way of coming up with inverse. Do you understand kind of the big picture? Okay, so let's talk about the sine. I also want to say one more thing before I get into the inverse, just so we don't lose sight of this. Okay, when I say sine of x equals y, when I write that on the board, are we all comfortable with the idea that what goes into a sine function is an angle? It's either in degrees or radians. And if you're using your calculator, you have to be in the right mode, right? But the argument of the sine function is an angle. The output is a what? A number, right? So think about it in this picture sense again. We have the domain, if this is the sine function, these are a bunch of angles living in here, right? And over here it spits out numbers. Now these numbers have to be between where and where? Think about the sine function. -1 and 1. Do you agree? So these are numbers between -1 and 1. Okay? And these angles can be anything. Right now they can be, can't they? Because sine, remember the graph of the sine function goes in both directions forever. But generally speaking, the argument of the sine function is an angle, and the output of the sine function is a number. So if I talk about its inverse, if I'm ever going to get an inverse for this function, what's going to go into it? A number or an angle? A number. And what's going to come out of it? An angle. Just always keep that in mind. When you're dealing with an inverse trig function, the angle comes out. A number is what goes in. It's the reverse of this. Okay, let's get to it. And that works for sine, cosine, tangent, cotangent, secant, all of them. So we are now going to talk about the inverse of sine. And we have to figure out a way to do it, right? Because we already talked about how when we graph sine, we've got this major problem that f of x equals sine x, if I draw it, is going to fail the horizontal line test miserably, right? So how do we cut it? Just like we did with the parabola, we need to cut it somehow. We need to restrict the domain. What we need, though, is to restrict it in a way that we get the entire range of the function. What I mean by that is, could I cut it? Just don't write this down, but could I cut it here and here and just look at that part right there? I mean, I could cut it, right? I could. But the problem with that is it's only going to give, oh wait, no, hold on, shit, I can't do that. That still fails the horizontal line test. I apologize. Sorry. I meant to say, like, if I did something like just like this part right here, okay? That would pass the vertical and horizontal line test. The problem is it does not include the entire range of the function. It doesn't have from -1 all the way up to 1. And what I'm trying to do is cut it in a way that I get the entire range in there. In other words, I need to go from like the bottom of the valley to the top peak, or I need to go from this top peak to the bottom of this valley. And I need to cut that appropriately so that I get that whole range out. So I'm going to do a better picture over here. Let me draw one period of sine, sorry. One period of sine, which we know this is the standard format for sine. So if I graphed this up here and I asked you to try and cut this thing up so that you could get the entire range in there, where would you cut it from? From where? Pi over 2 to 3 pi over 2? Let's see. I'm going to highlight that. Oh, I have a highlighter right here. No, this won't work. Better not use that. If I highlighted just between pi over 2 to 3 pi over 2, if I just did that, would that get me the entire range? Would I get all the values between -1 and 1 here? Yes. Would just that red piece pass the vertical line test? Would that red piece pass the horizontal line test? So that would work. So if I restricted that there, that would suffice. Now, that's not the only place I could do it, right? Someone else could walk in here and say, hey, look, what if you extend this out? Okay, like if I extend this out, let's go, here's 4 pi. Let me draw another piece here. So it would go up like this, down. And what would we have here? This is pi, 2 pi, this is 3 pi. This should be 5 pi over 2 right here, okay? This would be 7 pi over 2. So someone else would come in here, you know, and they're one of these people who don't want to conform, right? They just want to be their own, you know, they don't want to look like anyone else, they're just different, right? So they say, no, I don't like that. I don't like that red one. Instead, I would like to go from 3 pi over 2 to 5 pi over 2. Would that work? That would pass the vertical line test. That would pass the horizontal line test. That would include the entire range from -1 to 1. Wouldn't it? So that would work. And then someone else would be like, well, I want to be different too, and I want to do this one. And so you could like pick any little chunk as long as you get it, right? Yes? Any of those cuts would work. So there's going to be an issue. What if somebody, here's the red group, okay? What if the red group defines their inverse sine function based on this cut? When we plug things into the inverse function, it's going to spit back an angle, isn't it? And those angles are going to be between pi over 2 and 3 pi over 2. But then the blue group, when they use their inverse trig function, it's going to spit back angles between 3 pi over 2 and 5 pi over 2. And so they're actually going to be getting different answers, aren't they? And so what has to happen is we all have to come to the table, sit down, and agree on something. And long ago, we used to be able to do that, I guess, because mathematicians agreed we're all going to use the same cut so that there's no confusion, right? And here's the cut we decided to go with. It's neither one of those, all right? It's this cut right here. They actually went backwards. I'll draw it. Here's -2 pi. Here's negative pi. Here's negative pi over 2. Here's -3 pi over 2. And the graph goes backwards like this, comes back up, and goes back down like that, right? So here is the cut that we decided to go with. And I guess I'll use a green. It's the cut that goes from negative pi over 2 up to pi over 2. That's the winner. That's the one we use, all right? So now that we've got that settled and we all agreed upon it, let's talk about what the properties are of that particular cut. And what I'll do is I will graph it again here. Here's pi over 2, negative pi over 2. And we know that it looks like this. like that. This right here is the inverse function I'm sorry, no, it's not the inverse function. That is the piece we're going to use for the inverse function. All right, so I am going to take this sine function right here and now restrict its domain. And that's the restriction. So I would write the domain of this is going to be between where and where? Negative pi over 2 to pi over 2. Now this is extremely important that you understand that we've all agreed upon that domain restriction. Because if we go and try and draw like a picture of what's happening now, here's what we've got. They're starting to give us these new refillable markers. I'm really excited about them because they write really good, but they're hard to erase. They're just kind of, and I haven't had to refill one yet. That might be a nightmare. We'll see. Okay, so if I'm drawing pictures of what's happening here, this good old picture right here, where you've got your function here, sine. If I'm going to be able to define an inverse, this domain here can only have angles between negative pi over 2 and pi over 2. So you can only be pulling angles out of this set of angles. Yes? Now the output is still what? What's the range of this? It's still negative 1 to 1. I mean, we needed that to happen. We needed to get the whole range out, and we did get it, right? This was negative 1 down here, and this was positive 1 up here, so we do get the whole range. So when you send something back, look, when I take a number out of here and I send it back, I can only get answers between here and here. That's it. We good? All right, so let me see. Let's put some new notation up here. The inverse function of sine. Here it is. So there's sine. It's been restricted properly so that we can do vertical and horizontal line test. This is a picture of its domain and range. But how do we actually write the inverse function? We write sine with the little negative 1 of x. That's it. That is the notation that we use to tell everyone this is the arcsine function. Now I want you to compare that to the example I put on the board earlier. That was one of the examples I did, right? Where I did a restriction. We said, here's the function and here's its inverse, right? We were able to algebraically say what the inverse was. If this is the square function, this is the square root function, right? Two different functions. Here, there's no algebraic anything. This is just telling you, look, this is the reverse operation of sine. That's it. There's no algebraic thing you do. You have to understand how this works in order to do this. You'll see it when I put it in action. The other notation, you can put or here, and I very seldomly use this other notation, is to write arcsine x. And this function right here is known as the arcsine function. The arcsine, that's just what we call it. What does the arcsine function spit out again? Angles, right? Okay. And those angles have to be in here, right? We're about to do some examples. I'm trying to see if there's anything else I can do that's going to help us moving ahead here.
So this all dependent on what the work is telling us to do?
Is what dependent?
Like, I guess like finding the domain and range. Like I know you said this is the cut that we're supposed to use, but will it ever give us any other point? It's always just going to be this.
This is the one we agree on. Yeah, we had to because I mean, imagine you're doing your math over there in Europe somewhere working on some project, and I'm doing mine in America, and then we're using different cuts of arc sine. We're going to get different answers. You know, like we're never going to get the same thing. So that's the standard now. This is it. This is never going to change. For arc sine. For the inverse of sine, it won't change. Now, when we get to cosine, we're going to have to see if we want to cut it in the same place or not. I don't want to overload you here, but y'all remember the unit circle, right? Okay, look at this. Negative pi over 2 and pi over 2 are angles. Those angles are, here's 0, right? This is positive pi over 2. Clockwise rotation down is negative pi over 2. So what I know is that if I take a number and plug that number into the arc sine function or the inverse sine function, it's going to spit me out an angle that's going to be between pi over 2 and negative pi over 2. Pi over 2 and negative pi over 2. I am never, ever, ever allowed to go all the way around and come back into this quadrant, because that angle would be positive, wouldn't it? Like, what is like one of these standard angles? Isn't that 7 pi over 4? If that's that perfect diagonal right there. Isn't that 7 pi over 4? Of course, yes. Yeah, no, it is, okay. So that's 7 pi over 4. That could never be an answer for us. If we plug a number in here, we could never get 7 pi over 4 out, because that meant your angle went past pi over 2 and came back around, and now you have this positive 7 pi over 4. It's too big. So how would I represent that angle? Instead of going around, I would do what? Just go negative pi over 4, and that would give me the same thing. You'll see. We're about to do some examples. All right. We'll start out with something I hope that will be relatively easy. All right, first example. Find the inverse sine of root 2 over 2. Without a calculator. Well, there's a lot of different ways that you can approach this, all right? Here's one way that I'm going to approach it. This right here is equal to something, right? Why don't we just call it something? You can call x, y, theta. It doesn't matter. Maybe I can call it theta. Let's call it theta. Why should I call it theta? Because I know arc sine should spit out an angle, right? So I'd like to know what theta is. So that's basically this is telling you, hey, look, if you look at your unit circle and you only restrict yourself between pi over 2 and negative pi over 2, what angle are you plugging in to sine to get root 2 over 2 to come out? So sine is which coordinate on the unit circle? Y. The y coordinate. So this is really saying, where's your y coordinate, root 2 over 2? 45. At 45 degrees. Right? Right here, we have an x and a y coordinate. The y coordinate is root 2 over 2. So it's trying to figure out what is the angle that gave you that y coordinate to be root 2 over 2. And you said it was 45 degrees? So I could answer, the answer to this is going to be 45 degrees, or preferably in radians, pi over 4. And that's it. Do you agree that pi over 4 lives in here? Yes, it is. Is that pretty straightforward? Okay, let's try something else. How about we do arc sine of root 3 over 2? Root 3 over 2. So this is asking you on the unit circle, only looking between pi over 2 and negative pi over 2, where's the y coordinate, because it's sine, where's the y coordinate root 3 over 2? Right there, that's our theta. This is root 3 over 2, and that happens, that's one of our common angles, it's pi over 3, or 60 degrees. And is pi over 3 in there? Is it between negative pi over 2 and pi over 2? Yes. Is this pretty straightforward? I mean, this is not supposed to be complicated yet. Let's do another one. How about arc sine of negative 1/2? Okay, good. So we go unit circle again, not looking over here, only looking between pi over 2 and negative pi over 2. I want the y coordinate to be negative 1/2, which is that one or that one? Which one is it? The top one or the bottom one here? Or is it the one that's 45 right down the middle? Which one is it? It's this top one right here. It's this one. Because this has an x coordinate of root 3 over 2, but the y coordinate is negative 1/2. So we're looking at the y, right? So what is this angle? You could say negative 30 degrees, or you could say negative pi over 6. What can you not say? 330 degrees, you could not say. You could not say 11, why am I saying that? Yeah, 11 pi over 6, yeah, I was right. You could not say 11 pi over 6, right? Because that would be too big. So I'm going to go with negative pi over 6 or negative 30 degrees. So you just have to pay attention to what's going on. You happy? That's it. I mean, there's nothing more to this. Now, if we have something like, oh, well, yeah, let me try this one. What's arc sine of 0? What's arc sine of 0? That's asking you where, at what angle is your y coordinate 0? Isn't that right here? That's 1, 0, right? So the y coordinate is 0. So what is that angle? 2 pi, but isn't you can only be between pi over 2 and negative pi over 2. So 0. Make sense? Yes? 0. Now 0 degrees and 0 radians, you don't have to put degrees or radians because they're the same thing. All right, what would arc sine of negative 1 be? What's arc sine of negative 1? Doesn't that mean we're down at the bottom? Right? The y coordinate is negative 1 down here. So what is that angle? Negative pi over 2. Straight down is negative pi over 2. And remember, negative pi over 2 was in the domain. Remember where we made the cuts? The cuts were at negative pi over 2 and pi over 2. And the negative pi over 2, we needed it so that we could get that negative 1 to come out. What would arc sine of 1 be? Not negative 1, but arc sine of 1. Pi over 2. And that's because you're straight up. One more. What's arc sine of 1/4? You should be scratching your head a little bit here because you're trying to figure out where on the unit circle the y coordinate is 1/4, right? And unfortunately, that's not a common angle, is it? And so at this point, you would have to use your calculator, which we'll do later, all right? I just want you to see that so far, Everything I've asked you in terms of arc sine has been one of your common points on your unit circle, right? If I go outside of those common points, we're going to need technology to help us get the answer, right? But before we do that, let's talk about arc cosine. So I think I can go a little bit faster through arc cosine. The inverse cosine function start with a quick graph of the cosine function. And remember, this goes forever in both directions, right? Using the same philosophy, I guess so. Same ideas, all right? With what we had with the sine, we want our cosine function to take in angles, right? Angles here, and spit out things, and these still need to be between -1 and 1. But we need to take them back somewhere. When we did cosine, we decided -pi/2 to pi/2 would be where we take them back. What would be a nice appropriate cut here that would include the entire range? About 0 to pi would work, right? 0 to pi. Could you go from pi to 2 pi? Yes? And you could even go backwards, couldn't you? Well, the standard cut for cosine is actually that first one. It's the one that goes from 0 to pi. Right there. That's the one we use. Even though there's infinitely many that you could come up with, that's the one we all agreed on. So that means this angle that comes out, right, can only be between 0 and pi. So it's different than arc sine, isn't it? You have to pay attention to that. In terms of a picture of where these angles come from, on our unit circle, it's going to be between 0 and pi. So our angles can only come from here. The good news about cosine and its inverse is that we don't have negative angles. Right? With arc cosine, didn't we have an answer like -pi/4 or something like that? We will never have a negative angle come out of the arc cosine function. It's not going to happen. We're going to get 0 to pi and nothing else. And I think I can draw the notation of what it is. This one going back is just going to be the cosine with the little -1 of x. The other notation for this is arc, ARC, cosine, COS of x. These are our two notations that we use for them. And do you think you understand this to the point that I can just start giving you some examples? What's the difference going to be when I start giving you these numbers to plug in? It's only going to be 0 to pi, but you're going to be looking at something different, aren't you? Like when I give you a value, you're going to be looking at what on the unit? The x coordinate, right? Because it's cosine, you'll be looking at x coordinate instead of y. Yes? It's going to spit out angles still, yes. Because our cosine is going to take a number in, and it's going to spit back to us an angle. That angle is going to be between 0 and pi. All of these inverse trig functions, every single one of them we talk about, are going to take a number in and spit an angle back. Because the original trig functions take angles in and spit numbers out. So all the inverses will do the reverse of that. All right, here we go. What is arc cosine of -1? I'm just going to throw you right in. So don't give me an answer yet. Can somebody like verbally explain to me, like if I hadn't really very little idea of what I was supposed to do here, like what you're thinking through mentally to get to this answer? Go ahead. You sound like you're ready to verbalize that.
I guess like just to like side to side. Maybe.
Okay. So, do you know the answer?
No.
No?
My guess is 0.
Okay. Where are you getting that from?
From because cosine is x.
Cosine's the x-coordinate.
Yeah.
So this is asking you, where is your x-coordinate? -1 on the unit circle. It wants you to go look at the unit circle. It wants you to cut off the bottom quadrants because you're talking about inverse cosine. So you automatically throw those out. And it wants to know where on this unit circle your x-coordinate is -1. At pi. Here, right? That's where your x-coordinate is -1. What is the angle, right? What is the angle that gets you to that point? The angle is pi. Make sense? How about this one? Arc cosine of 0. Okay, so no answer yet. Out. I'm letting you all think. And get a little more of this. It's Thursday, right? All right. Can somebody verbalize what they're, like, don't just give me the answer, but can you explain like what your thought process is here when you see that? Anyone? Go ahead.
Where is x going to be 0? That's what I go in thinking. Okay,
Mhm.
so we're on that unit circle.
Where on the unit circle is,
Right. So then I just go, okay, it's going to be 0 at the top.
okay,
Right. So then I go, okay, what angle is it that corresponds to that point?
that's exactly it. Okay? You're saying, because it's our cosine, you're saying I'm looking at the x-coordinate on the unit circle. Want to know where on the unit circle the x-coordinate is 0. Now you said it's at the top, right? Why didn't we look down?
It's at the bottom, but that's no-go territory.
Yeah, that's right. This is no-go territory, so you can only look up here, right? It can only be there. And then that very last part that you said is the real important part, is you said, and then what's the angle that gets me there, right? Like, what is the angle that gets me to that point? And that's going to be pi over 2. Now, there is a way you can check your answer. You can just take that answer and plug it into cosine. Take pi over 2, plug it in cosine, and then you're doing the reverse. You're saying, okay, go to pi over 2 and give me the x-coordinate. It's 0. It matches, right? Pi over 2 goes into cosine, it spits out 0. 0 goes into the inverse cosine, spits out pi over 2. So it takes it back to where it came from. How about this? How about arc cosine of -√3 over 2? So you're saying, okay, I'm looking at just the top half of the unit circle. I'm looking at the x-coordinate, trying to figure out where that x-coordinate is -√3 over 2. And because I have mastered the unit circle, right, so you remember I was trying to get you all to really get like intimately related to that and like comfortable with that unit circle? It's because this stuff is a lot faster when you can see the unit circle without having to pull that piece of paper out. That takes time, I understand. So where is it? It's right there, right? It's right there? Okay, so we have three important points over here, right? We have this one, halfway, and this one. And it's this one, isn't it? Because that has the coordinates negative root 3 over 2, positive 1/2, but we're only looking at the x coordinate. So the angle that corresponds to this is what? It's 150 degrees. But in radians, what is it? 5 pi over 6? That's it. 5 pi over 6. Do you need more examples, or you think you're comfortable? Yes?
So from this section, we're not going to have any that you need your calculator to figure out? They're all going to be...
Yeah, we will. We'll do some with calculator, just not quite yet. Yeah. I'm saving that till we first get through all. We're going to only do sine, cosine, arc, cosine, arc, sine, arc, cosine, arc, tangent. We're not going to do the other three. All right, how about this one? Cosine inverse of 3. Haven't given you one like this yet. Try and verbalize it. At what angle is the x coordinate 3, but where are you looking for that? You're supposed to be on the unit circle, aren't you? But that's not on the unit circle. Right? Our unit circle looks like this. This is 1, 0. This is negative 1, 0, right? So this has a radius of 1. We knew that. That's why we called it the unit circle. And we're saying, where's the x coordinate? 3, that's out here.
Well, it's still going to be the same, right? Like, even if, because the angle still goes the same way?
Yeah, so you might think the answer to this is 0, because that 0 degrees would take you out there, right? There's a problem. Yeah. Remember this picture? We said for arc cosine, for cosine we're going to restrict the domain. And what were the outputs between where and where? Negative 1 and 1, right?
Right.
And then go back, and what am I asking you to do? Take a number that's not in here and plug it in. Can't. So this is undefined. It's a tricky question. That's why I'm showing it to you now instead of like on a test, right? This is undefined. You cannot plug negative 3 into the inverse cosine function. If you have a calculator out and you've been kind of trying this, you can actually try and type in, if you know how to do the inverse cosine, type that in and it's going to give you some sort of error. Domain error? Yeah, so it already knows you can't plug that in. If you want another picture, remember we took the cosine function and we cut it off here, right? We took this cut and we were trying to figure out at what angle the value was 3. Remember, this is 1. We were trying to figure out where the value was 3. But this function is never up at 3. Like it's stuck between negative 1 and 1, so it can't ever be there. So in other words, if I plug any number in here that's bigger than 1 or less than negative 1, it's undefined. So arc cosine of 2 would be undefined. Arc cosine of negative 0.5 would be, negative 0.5 would be defined. Negative 2.5 would be undefined. All right. Time to give you the dangerous cancellation properties. The book does not call these dangerous, but they are. Here's what the dangerous cancellation properties say. They say this. First, the first cancellation property says this. Sine of arcsine of x equals x. And the next one says that arcsine of sine of x equals x. Now, what this should look like to you is what I put on the board earlier. When I said, here's the real definition of what it means to be inverse functions from college algebra, that if you plug in, oh, I put that on the board. That if you plug in x and it goes through one and then loops back over, it'll go back to where it came from, right? That's what I had shown you. That's what these two properties are saying. But one of these properties is extremely dangerous. Let's see if we can figure it out, which one is dangerous, okay? Let's see if we can. I'm going to leave a little space here. I'm going to add something to those properties. But I want to give you some examples first. Let's see if we run into any problems. All right, first example. What is sine of arcsine of hold on a second. Root 3 over 2. I'm looking, that looks a lot like the first property, right? Sine of arcsine of x. The answer should be x, so it looks like the answer should just be what here? Root 3 over 2, right? This looks like it should be root 3 over 2. All right, I'm going to leave that as a question. Let's see if it really is. Tell me what this is, which is what we were just doing, right? So you go through this mental exercise. You're saying, I'm looking on the unit circle. I'm looking at the, which coordinate? The y coordinate. I'm only allowed to look between, so I'm sitting here on the unit circle. I'm only allowed to work between pi over 2 and negative pi over 2, right? Looking for a y coordinate of root 3 over 2, which would be up here, right? And that, what angle is that? Pi over 3. Okay, so this is really saying, this right here is really saying sine of pi over 3, isn't it? Okay, now let's start over. If I just threw this out there for you, said, hey, what's sine of pi over 3? What you would say is, go to pi over 3 and tell me the y coordinate. And what would the y coordinate be? Root 3 over 2. So I guess what I'm getting at is this piece right here, right, all of that, all of this right here, this thinking just produced that pi over 3, right? And then we just took sine of that pi over 3 and got this. So look, it looks like it works. Doesn't that look like that worked okay?
So basically, whatever you plug into x inside is answered.
Sometimes. As we're about to see. That's why this is why this is dangerous, okay? All right, let's try another one, all right? I want to do another one of these. Let me change it up a little bit. Okay. How about sine of arcsine? Let me try and throw a negative in here, see if it screws it up at all. Negative 1/2. You know, let's make that negative root 2 over 2, just because I don't think we've used root 2 over 2, have we? Oh, we have? Okay, well, let's just do it anyway. Negative